in the Netherlands. First, I'd like to thank the organizers for giving me an opportunity to talk here today. Today, I'd like to talk about the effects of UV radiation intensity, metallicity, and Eddy diffusion on transmission spectra of hazy exoplanet atmospheres. First, as you know, recent observation of transmission spectra reveals the diversity of transmission spectra. This is a figure from Singh et al. 2016, and this shows the transmission spectrum of 10 hot Jupiters. Horizontal axis shows the wavelength in micron, while the vertical axis shows the normalized transit depth. You can see that some of planets show the very scattering slope in the optical. On the other hand, in the near-infrared wavelength range, some show very distinct molecular absorption features of water, or some spectrum are very flat or features. These facts suggest the existence of aerosols in the atmosphere of some exoplanets. There are two types of aerosols, condensation clouds and photochemical haze. In this talk, I'd like to focus on hydrocarbon haze particles. Let me explain the production process of hydrocarbon haze first. First, precursor molecules of hydrocarbon haze are created through photochemical reactions triggered by the photodissociation of methane. Then particle growth takes place and results in large haze particles. In Kawashima and ECMO 2018, we modeled the haze formation processes, both photochemistry and macrophysics. Using the photochemical model, we derived the distribution of precursor molecules of haze particles. And also using the derived distribution of precursor molecules, we derived the haze distribution in the atmosphere. Also, I modeled the transmission spectrum models. In this talk, I'd like to explore the effect of UV radiation intensity, metallicity, and Eddy diffusion, because these three parameters are very important for haze formation processes. Let me describe our models briefly. In this talk, I'd like to, I will use the three models: photochemical model, microphysical model, and transmission spectrum, which we developed in a previous paper, Kawashima and ECMO 2018. First, for photochemical model, we consider 29 species composed of these 5 elements: carbon, hydrogen, oxygen, nitrogen, and helium. We consider 300 thermochemical and 16 photochemical reactions. As for temperature pressure profile, we use the analytical solution of GERO 2010. And for UV spectrum, we use the constructed UV spectrum for GJ1214 measured by Youngblood et al. 2016. For elemental abundance, we take the solar elemental abundance ratio from DOTA 2003, and for the Eddy diffusion coefficient, we assume this value for the fiducial case. And next, for microphysical model, we derive the distribution of haze particles of multiple sizes by considering particle growth, sedimentation, and Eddy diffusion transport. And for monomer production rate, so monomer is the minimum size of the particles considered inside the model. We consider monomer production rate as the sum of the photodissociation rates of haze precursors, methane, HCN, and C2H2. Finally, for transmission spectrum, we calculate the transit depth at each wavelength with this equation. We calculate the opacity of each molecule using the Hytron database, and for refractive index of haze particles, we use a measured value of Carey et al. 1984. Before going to the details of the results, I'd like to first show the results for the photochemical calculations for the fiducial case. So the left figure shows the distribution of volume mixing ratio of each molecule as a function of pressure in bar. And the right figure shows the photodissociation rate of each molecule, also as a function of bar. You can see that hydrogen, CO, H2O, and NH3 are the major stellar photon absorbers via photodissociation. Also, among the haze precursors, I mean methane, HCN, and C2H2, C2H2 photodissociates most in spite of its lowest abundance. This is because unlike methane and HCN, C2H2 can use lower energy photons for its photodissociation. Next, I'd like to move on to show the results of the dependence of the transmission spectrum on UV radiation intensity first. So these two figures show the distribution of gaseous species for high UV radiation intensity case and low UV radiation intensity case. As you expect for high UV radiation intensity case, photochemistry occurs very efficiently. On the other hand, for low UV radiation intensity case, photochemistry is very inefficient, and the volume mixing ratio of each molecules are almost determined by mixing. And as for the photoassociation rate of each molecule, you see that the photoassociation rates of each molecule are larger for high UV radiation intensity case because of the larger incoming photon flux. And for the photoassociation rates of Hazy precursors, you see that for high UV radiation intensity case, the photoassociation rate of Hazy precursors are also larger. So in summary, production rate is larger for high UV radiation intensity case and smaller for low UV radiation intensity case. And these two figures show the distribution of Hazy particles for high UV radiation intensity case and low UV radiation intensity case. First, the vertical axis shows the pressure in bar, and the red line shows the average particle radius, while the orange line shows the number density of Hazy particles. Also, I plot the monomer production rate with green lines and the mass density of each particle size with blue color contour. You see that for high UV radiation intensity case, both the average radius and the mass density are larger. This is just because the monomer production rate is higher for high UV radiation intensity case. On the other hand, for low UV radiation intensity case, you see that both the radius and the mass density are very small because the monomer production rate is small. So the Hazy is abundant for high UV radiation intensity case and less abundant for low UV radiation case. And this figure shows the transmission spectrum for different UV radiation intensity case, from low UV radiation intensity case to high UV radiation intensity case. You see that the differences in UV radiation intensity can explain this recently observed diversity of transmission spectra. So in the optical wavelength range, the low to modest UV radiation intensity shows the Rayleigh scattering slope in the optical. On the other hand, in the near-infrared wavelength range, some low UV radiation intensity case show absorption features in their spectrum. On the other hand, high UV radiation intensity case, the spectrum are very featureless or flat. Next, I'd like to move on to the second parameter, atmospheric metallicity effects. So these two figures show the distribution of gaseous species for 1 solar case and 100 solar case. As you expect, in the case of 100 solar metallicity case, volume mixing ratios of all the molecules other than hydrogen and helium are increased. And next, these two figures show the distribution of photoassociation rates of each molecule for 1 solar and 100 solar metallicity case. You see that in 100 solar metallicity case, the carbon monoxide and NH3, H2O, and hydrogen and O2 photoassociation rates are larger compared to the 1 solar case because their abundance has increased. So for Hazy precursors, photon shielding effects by these molecules, so water, carbon monoxide, CO2, and O2 existing at higher altitudes than the Hazy precursors are increased. So because of this photon shielding effect, we found that the photoassociation rate of Hazy precursors are smaller for 100 solar metallicity case, even though their abundance has increased. So we found that the production rate of the Hazy precursors are smaller for higher metallicity, even though their abundance has increased. And this figure shows the transmission spectrum for different atmospheric metallicity. So the green line shows the 1 solar, 10 solar, 100 solar, and 1000 solar metallicity cases. And the thick lines show the spectrum for the Hazy case, while the thin lines show the spectrum for the Hazy-free case. And the horizontal axis shows the wavelength in micron, while the vertical axis shows the depth in percent. We found that at relatively short wavelengths, less than a few microns, we found that the absorption features are more the largest for moderate metallicity, such as 100 solar metallicity. This is because of the two competing effects. One is production rate, and the other one is atmospheric scale height. Because we found that both the production rate and the atmospheric scale height are smaller for higher metallicity. So because of these two effects, we found that the absorption features are the largest for the moderate metallicity, such as 100 solar metallicity case. Also, on the other hand, for the long wavelength region, we found the dependencies is rather simple. Because the haze particle does not affect the long wavelength so much, we just found the absorption features are larger for lower metallicity. And some of you might have realized that the dependence we have found is the opposite from those recently found from the experiments. So this figure shows this figure is from Horsted of 2018, and they conducted their experiments and measured the production rate of haze particles inside the chamber as a function of temperature and metallicity. They found that the production rate of haze particles are higher for higher metallicity. On the other hand, we showed that the production rate is smaller for higher metallicity. This is because of the production, the mechanism we considered or taking place is different. So for chemistry, the chemistry occurring in the experiments are very complex. On the other hand, the chemistry we can model is rather simple, I would say. And also, on the other hand, for the vertical effect, which we found is very important and is not considered in experiments. And we found that for the modelings, we consider these effects. So I'd like to point out that combining both experiments and modelings are very important, even though it's not so easy to combine these two different approaches. So we have to seek out a way to combine these two experiments and modeling. Next, I'd like to move on to the third parameter, so eddy diffusion coefficient. These two figures show the distribution of haze particles for the fiducial eddy diffusion coefficient case and large eddy diffusion coefficient case. Again, the vertical axis shows the pressure in bar, and the red line shows the average particle radius, and the orange line shows the average number density. We also plot the mass production, monomer production rate with green lines, and the mass density of haze particles on each side with a blue color contour. You see that for a larger eddy diffusion coefficient case, we found that both the average radius and the mass density of haze particles are smaller. This is because of the eddy diffusion transport. We found that the efficient eddy diffusion transports the haze particles downward rapidly. So it means it removes the particles from the upper atmosphere. We also modeled the transmission spectrum model. So again, the horizontal axis shows the wavelengths in micron, and the vertical axis shows the depth in percent. And the green line shows the spectrum for the fiducial eddy diffusion coefficient case, whereas the purple line shows the smaller eddy diffusion coefficient case. We found for the larger eddy diffusion coefficient case, it produced a very distinctive eddy scattering slope in the optical. This comes from the very steep gradient of the mixing ratio of the haze particles in the atmosphere. Also, you see that there is not so much difference between this fiducial case and Lloyd case. This is because for these values of eddy diffusion coefficient, eddy diffusion transport does not play a role for the distribution of haze particles. So I'd like to summarize my talk. We explored the effect of UV radiation intensity, metallicity, and eddy diffusion transmission spectra of hazy exoplanet atmospheres. First, for UV radiation intensity, we found that the differences in UV radiation intensity can explain the observed diversity of transmission spectra. Next, for atmospheric metallicity, we found that the absorption features are the largest for moderate metallicity at short wavelengths. But I have to point out that we need to combine both experiments and modelings very carefully. And finally, for the eddy diffusion coefficient, we have found that efficient eddy diffusion produces very steep radius scattering slope in the optical. Thank you.
So, one question here first.
Thanks for the talk. I have actually two small questions. So firstly, when you changed the solar flux intensity, did you do it in a steady state conditions? Did you try to model like pulse-like increases in solar radiation? And if so, does it have any lasting effects on the composition?
So in this case, I just assume the steady state conditions. So, but I think the chemical timescale for haze formation is very small. So if there's a flare of a cluster, I think it can affects the chemistry to some extent. But I found the distribution of haze particles, it takes a time scale for the haze particle growth much larger. So I think that it takes about almost 1 year from the top atmosphere to the downward to the lower atmosphere. So I think unfortunately, for haze particles, unless the production rate is very large, I think the UV flare does not impact the spectrum so much.
And actually, on the timescale question, is using Eddy diffusion a good approximation for such a model in terms of what are the timescales of diffusion versus the UV irradiation for this atmospheres?
So the Eddy diffusion transport timescale is very large compared to the chemical timescale. So it's like more than 1 year or so. It's very large.
So one question by Nick, and then Jeremy for the last question.
Thank you. That was really interesting work. So do we know the UV fluxes from the stars in the SING et al. Sample? And is the variance in UV flux of those stars comparable to what you did in your simulations?
Sorry.
So you basically showed that you could explain the SING, the variance in the transmission spectra from the SING et al. Paper by varying the UV irradiation. And do we know the UV flux impinging on those different planets?
So for currently, we only know the 10 hots. We know the UV spectrum for only 10 projectors, 10 hosts of 10 exoplanets or so. So we cannot observe UV spectrum for the very distinct star. But I think that if the test discovers the nearest exoplanets very much, I think the samples of the host the UV spectrum observation is increased. So I think we can explore more about the UV effect.
Jeremy?
Hi. This is a really interesting effect that you see the reverse, where in the experiments, more metallicity means more haze, and it's the reverse in the model. Do you think it's due to the more complex chemistry, or do you think it's more due to a shielding effect from the upper atmosphere that is not in the experiment?
So I think that there are several effects responsible for the different effects. So first, I'd like to say that for experiments show the production rate is higher for higher metallicity, and this means the conversion efficiency. So conversion efficiency from the methane to final hydrocarbon haze are larger for higher metallicity. And this effect we cannot in our modeling we just assume the 100% conversion efficiency because we don't know the dependence on the metallicity. And also I'd like to say that for the vertical effect cannot be considered in the experiments. So for the photon shielding effect, I found that it is larger for higher metallicity. So I think that this is an opposite competing effect. So we have to consider both effects carefully.
Thanks again.
Thank you.